This video will cover Chapter 3, Sections 2 and 3 of Describing Data Numerically. So we've covered measures of center and location in the box and whisker plot in the last video. In this video, we're going to cover measures of variation and explain what they mean, compute the coefficient of variation and z-scores, and apply these to statistical problems, and understand the empirical rule and apply it. So we've covered the left 2/3 of this. So we're going to focus on these measures of variation. So we'll start with range and interquartile range, which we've already talked about a little bit. Then we'll go on to variance, standard deviation. Both of those have a population formula that's different from the sample formula. And then we'll talk about coefficient of variation and z-scores. When we talk about variation, what we mean is how much spread is there in the data. If you have a set of data where all the data points are not the exact same value, then there's variation in the data. There's spread in the data. So these different measures of variation are going to give us different measures of spread, how far apart variables are in the data. All of these measures of variation have a similar characteristic. The smaller the value, the less variation there is in the data. The larger the value, the more variation there is in the data. So we've got an example here of two different curves that have the same center, so the same mean, but they have different measures of spread or variation. So we've got the tall, skinny guy. He's going to have a small measure of spread, and the short, fatter guy, he would have a larger measure of spread or variation. We've actually calculated range already when we were doing the histogram. This is the simplest measure of variation. All we have to do is find the maximum value, the minimum value, and find the difference between. So in my example here, I've got the lowest value is 1, the largest value is 14, the range is 13. We just take 14 minus 1, and the difference between those two, or the deviation, or the spread, is 13. One of the problems with range is that it ignores how the data are distributed between that minimum and maximum number. So this distribution on the left is spread out very evenly between 7 and 12, and we get a range of 5. This distribution on the right is really clumped to the end towards the 12, but we still get only a range of 5. The other issue is that the range is very sensitive to outliers. So we've got two very simple sets of data here, a bunch of 1s through 5. 5 minus 1 is 4. What if we just change 5 to 120? 120 minus 1 gives us a range of 119. So the number is very sensitive to outliers, and we have no idea what's going on between the two endpoints. One of the things we can do to eliminate the issue of having outliers cause that value to change significantly is focus on the interquartile range. It's going to cut off, remember, the bottom 25% and the top 25% of the data. So the interquartile range is Q3 minus Q1. It focuses on the spread of the center 50% of the data. So an example here, we've got a data value at a minimum of 12 and a maximum of 70, and we could find the range. But if we're going to focus on the interquartile range, we'll ignore those and just look at Q1, which is 30, Q3, which is 57. 57 minus 30 tells us there's a 27 unit spread between those two values, or across the center 50% of the data. So we're going to spend a little bit of time on this slide talking about variance, but we'll also talk about notation and Greek versus Roman letters to make sure that you've got all these little bits under your belt. So let's start with what variance is, and as we go through that, I'll point out some notation things for you. So this says that the variance is the average of the squared deviations of values from the mean. This note here in squared units is just to remind you that what we get out of this formula is going to be in squared, like feet squared or dollars squared. We've got population and sample again, and that's going to be important as we go through the formula. What I want to point out for you is that population is always associated with Greek letters. So in this case, the population variance is denoted by the Greek letter sigma squared. Sample is always associated with Roman letters. The sample variance is denoted by S squared. The squared, to remind us that we're talking about squared units, and we've squared all this stuff that we're entering into the formula. So let's start off with this word deviation. Deviation of values from the mean. So what does that mean? That's how far apart two numbers are. So if I'm looking at this center part, xi minus mu, well, that minus tells me I'm going to look at how far apart these two numbers are. The xi represents the individual data values. The mu represents the mean. So the center part of this is actually the deviations of the values from the mean. How far apart is each value from the mean? Notice it's the same thing down here, but we've replaced the population mean with the sample mean. This says squared deviations, so we've squared those deviations. Now, why do we do that? We could just average out all the deviations to get a sum here. But the problem is, if we add up all the deviations, we actually get a sum of 0. That's not going to give us any information. So we could take the absolute value, but we don't do that. If we took the absolute value and we added it all the values would be positive, and we'd still get a positive number. But we square these instead. And the reason we do that is, 1, it will make all the values positive, but 2, it will make those values that are outliers, the guys that are way far away from the mean, have a bigger weight when we sum this up. Remember, if a number is way far away from another number, when we subtract it, we get a big number. When we square it, that number grows exponentially. So we square this to give bigger weight to those values that are far away from the mean. What that's going to actually do is make our measure of spread really big, but that's okay. That's what we want. We want to know there's a chance of being way far away from the mean. Now, this sum guy we've seen before, this just means add up all of these deviations of each of the individual points in the population, or in this case, in the sample. And then we've got this word average. So we're adding all these things up and we're dividing by the number of items in the population. If you're kind of comparing these, as you should be while I'm talking about it, you notice that here we're dividing by the number of items in the sample, but we're subtracting 1. So we do this n minus 1 for a very particular reason. Notice in our deviation up here, we have this sample mean. That sample mean is an estimate. We already know that number is wrong. It's not the true population number. So we've already made an estimate. We want to be sure as we calculate the sample variance that it represents as well as possible the population variance. But because we've used this number in here that's wrong, we want to divide by a smaller number to make the fraction bigger, so that our sample variance will likely be bigger than our population variance. But it helps us to account for the fact that we've already used an estimate in our calculation. Now, I said we divide by a smaller number to make the fraction bigger. Let me just have you think about that for a second here. Okay, so let's pretend that n is 10 and our summation on the top was 100. So if we just took 100 and we divided by 10, we'd get 10. If we divided by n minus 1 instead, we'd divide by 9. That 9 would give us 11.1 repeated. So we'd get a bigger number. And that bigger number would just help us be sure that we're talking about a spread that accurately represents the data. Now, we don't usually use the variance when we talk about spread in the data. We usually use the standard deviation. Notice standard, because it's the measure we use regularly. We use the standard deviation because it takes us back to the original units in the data. So let me explain really quickly how we calculate it, and then I'll show you how it uses the original units from the data. Population standard deviation. Notice we've got sigma, but it no longer has the squared on it, because what we've actually done is take the square root of that variance formula that we used before. So this is just the square root of what we've calculated in the previous slide. It's the same for the sample standard deviation. Notice S no longer squared, and this is the square root of that formula that we saw again in the last slide. So let's think about this. When we were looking at the variance, we plugged in numbers and we squared them. So I'll use the example of throwing discus. In high school, I threw discus. When you throw discus in high school, they measure your throws in linear feet. So I could have calculated my variance in my throws. I didn't get a lot of good training, so there was a lot of variance in my throws. So I could calculate each individual throw minus my average throw and square that. Well, because it's in feet, when I square that, it becomes feet squared. If I'm trying to talk about a measure of spread, feet squared doesn't make a lot of sense when you're throwing discus in a straight or straight-ish line. Feet squared would be a measure of area. But if I come over here to standard deviation and I take the square root of that, I'm back into feet. Now I can talk about feet, and it's something that makes sense. We actually understand feet and feet squared, even though feet squared wouldn't make sense for my discus throws. But I have actually no comprehension of dollars squared. So we like to use the standard deviation because it always takes our units back into the units from the original data. Here's an example of how to do this by hand, but we've got a sample of data. The average of those data values is 3, and there are 10 data points. So what I did here was go through and fill in the x sub i's with each of these individual data points. So x1 is really 4, x2 is 7, and so on. For each of those, I'm going to subtract the mean and square it and then add them together and divide by 10 minus 1 when I get that all done. So I went here and I filled in the mean. 4 minus 3 squared plus 7 minus 3 squared, and down the line here, divide by 10 minus 1, and then I'll take the square root of that. So if we do a little simplification, we get 54 on the top, divide by 9, that's the square root of 6, which happens to be 2.449. Okay, standard deviation is one of those measures that can seem a little bit confusing or nebulous. What is this thing all about? So I wanted to use a picture here to help us start to get a sense of what different values of the standard deviation would tell us. So we've got 3 different data sets here. Each data set has a mean of 15.5. So we're comparing data sets with the same mean, but each of these has a different standard deviation. So you can see data set A has a standard deviation of 3.338, B has a standard deviation of 0.9258, and C has a standard deviation of 4.57. Let's start with data set B. Notice all the data are lumped really closely together, right around 15.5. And it has the smallest standard deviation, only 0.9258. So when the data values are lumped really closely together, they're not very spread out, and they have a small standard deviation. As the data set begins to get more spread out across the number line, we see the standard deviation begins to go up. So this standard deviation is 3.338, bigger than our 0.9. And notice if we lump the data all the way at the ends of this number line here, our standard deviation gets even bigger. The more spread out the data, bigger the standard deviation. Now, section 3 puts together stuff from section 1 and section 2. They entitled this section Using the Mean and Standard Deviation Together because we're going to talk about a couple of ways that we can use those two things together to say some more stuff about our data. So the first thing from this section is the coefficient of variation. The coefficient of variation, or I often just call it the CV, is defined as the ratio of the standard deviation to the mean expressed as a percentage. Okay, so what does that mean? It means take your standard deviation and divide by the mean. Okay, so that's what ratio of the standard deviation to the mean means. Take your standard deviation, divide by the mean. Notice I'm looking at Greek letters here, so this is representing the population. Multiply it by 100 to turn it into a percent. What this is actually saying is how big is the standard deviation as a percent of the mean. This is the sample notation. We would take the sample standard deviation and divide by the sample mean, multiplied by 100%. Now, when do we use this? We want to use this when we're trying to show relative variation. So anytime we have data sets that have different means, but we want to talk about which one has more variation in it, hence the word relative variation. we want to use the CV. So if I ask you a question that is about relative variation, you should automatically go to the CV. Here's an example so that you can try to make some sense of this. I'm risk averse, so I'm always looking for which stock is going to be relatively riskless. We know that stocks aren't riskless, but relatively riskless, because I want to look for the stocks that aren't going to have as much variation in them. So stock A has an average price of $50 last year. So that's our average, a standard deviation of 5. Stock B had an average price last year of $100 and a standard deviation of 5. Now, we don't have the same means, so the only way we can talk about relative variation here is to use CV. We're going to take the sample standard deviation, divide by the mean, multiply it by 100% to turn it into a percent. So $5 divided by 50 times 100 is 10%. 5 over 100 times 100% gives us 5%. Both stocks have the same standard deviation, but stock A is relatively more risky, has relatively more variation in it, right? That 5 is bigger compared to 50 than 5 is compared to 100. Another way that we'll put the mean and standard deviation together is for something called the empirical rule. So the empirical rule is used to just give us a sense of where the values are in a data set. Also, it can tell us about how likely a value is to occur. So if a data set is approximately bell-shaped, doesn't have to be perfectly bell-shaped, but if it's approximately bell-shaped, then we know a few things about how the data are distributed. So this mu plus or minus 1 sigma really just means take the mean and add a standard deviation to get an upper bound here. Take the mean, subtract a standard deviation to get a lower bound here. If we go from the mean, down 1 standard deviation, and up 1 standard deviation, we know about 68% of our data should lie inside those boundaries, lower and upper boundaries. If we go up and down 2 standard deviations, so like the green guy here, we know about 95% of our data should lie inside those 2 boundaries. And if we go out 3 standard deviations, like the orange picture over here, so we've taken the mean and gone down 3 standard deviations and taken the mean and gone up 3 standard deviations, we know almost all of our data will lie inside those 3 standard deviations. Now, I said I use this sometimes to think about probability. If I find that a data value is more than 2 standard deviations away from the mean, right? It's outside this 95% interval here. I think, wow, that data value is way far away from the mean. It doesn't have a really big chance of happening, right? Being far away from the mean is not very likely. So if I'm outside 2 standard deviations, I know that data value is not very likely. If I'm outside 3 standard deviations, I know that data value is extremely unlikely. So the empirical rule can help us know where the bulk of our data is, but can also help us understand that data values are fairly likely or not very likely to occur. So let's use an example here of the empirical rule. We've got customer age for a major retail chain. Suppose that it's bell-shaped with an average of 43. We know that the standard deviation is 7. Suppose that we want to know the age range for the majority of our customers, and let's define that majority as 95%. So if it's 95%, I need to go down 2 standard deviations and up 2 standard deviations to calculate my boundaries. So the lower bound would be the mean, 43, minus 2 times the standard deviation, which is 7. So 7 times 2 is 14. 14 from 43 is 29, and I get the lower boundary on my 95%. The upper bound would be 43 plus that same 14, so I would get 57 as my upper bound. I know 95% of my customers, or the majority of my customers for this retail chain, are between 29 and 57 years old. The last section of this chapter covers something called standardized data values, or what we're going to call Z-scores. Standardized data values has a very particular meaning behind it. When we standardize a data value, what we're actually doing is just finding out how many standard deviations that value is from the mean. So if we look at the formula here, again, we have population and sample formulas. All we really do is replace the population values with the sample values. The z-score is going to tell us the number of standard deviations the value is from the mean. So we'll look at the top again, like we did with variance, and actually notice that it looks kind of the same. The top part of this, x minus mu, is almost what we saw on the top of the variance formula. This is actually just a deviation. How far away is x from the mean? So if x is above the mean, we're going to get a positive number here, and this is going to tell us how many units x is above the mean. When we divide by the standard deviation, we're saying how big is this deviation in a number of standard deviations. It's the same exact concept here. How far is this x value from the sample mean divided by the sample standard deviation? So how many standard deviations in sample terms is this value from the mean? This z-score is going to be really useful. We can actually use it to say how many deviations a value is from the mean, and is that value then very likely to occur or not? So we've got an example here. IQ scores in a large population are approximately bell-shaped with a mean of 100 and a standard deviation of 15. Suppose that you went online and you took one of those IQ tests, and it gave you a value of 121. And you said, okay, 121, so what? You want to know what that means? Or how did you do then really relative to everybody else? One of the things you can do to talk about that is to calculate the z-score. So how many standard deviations above the mean are you if you scored a 121? 121 is our x, so we plug 121 in where the x is. 100 is the mean, so we plug that in where the mean was. Then we divide by 15. So the top of this gives us 21. Your IQ score of 121 was 21 points above the mean. 21 divided by 15 says that 21 is actually 1.4 standard deviations. It's 1.4 of these 15s. So you're 1.4 standard deviations above the mean. Not too shabby.